Hey,
Hey, Manzelos, how's it going?
pretty good. How about you?
I'm good. I'm good. How's teaching been going?
Well, not good, not bad. But I mean, I wish it was in person, but it's not that terrible. I think
Yeah.
I'm at the point where I don't have to think about this and feel bad. So that means that it's going well, I guess.
Yeah, true, true.
What about you?
Yeah, it's been, this is the only time I taught has been online, so I don't have a frame of reference to compare it to. But this semester's been fine. It's just like twice the amount of work since I have two sections. So I spending too much time on these two classes. I don't know. I like
Well,
I
don't. I mean, try to avoid.
yeah, yeah, I agree. I don't know how it ends up like that. Yeah, it's just the quiz, it's just the grading, really, honestly, because I don't even grade the worksheet homework. It's just the quizzes. But I have a quiz like essentially each week, and that takes a lot of time up.
So I usually have less. I put less work. So, for example, this semester, I started giving them homework every Friday. But after 3 Fridays, I got bored, and I will not give them my homework until the first test. So
Ah, gotcha. You also said, I think I remember you telling us that you do less quizzes in the semester, right?
yes, I've done no in class quizzes and only one which was take home.
Oh, okay, that must be much better in terms of grading.
Yes, I don't know how much better it will be when the exam comes, but
Yeah,
yeah, at least I spend
they'll
too
find out,
much
I
time
guess.
on it. Yeah.
Yeah.
Hey, how's it going?
Hello.
All right, it's been a very busy week again. How did that happen? All right, any questions? No? All right, I decided don't really know why, I guess it doesn't matter. I decided to temporarily skip ahead a little bit. We had finished chapter 2 except for a discussion of cup products. But we don't really need cup products right away. So I decided to look to see what chapter 3 was. And I don't know, I found myself more enthusiastic somehow about the material of chapter 3. I feel like it's actually doing something in Gawa Chromology. It's not just all these kind of definitions and very formal things. So yeah, so chapter 3 is about certain topics that culminate in this Tate Nakayama theorem, which does involve cup products. And so yeah, so I think I also, let's see, I have a little over 9 pages of written notes, so I doubt that. I think that's probably more than one lecture. But anyway, so I want to cover. I think I want to cover most of chapter 3 in a fair amount of detail. Seems nice. And then we'll circle back to define cup products, state without proof some kind of formal properties of cup products that are treated nicely in chapter 2, and then we'll come back and have some discussion of the Tate Nakayama theorem. This is all very much in the French style, by the way. Like the Tate Nakayama theorem is a very specific result about cup products of cohomology classes and blah 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 blah. And you look at it and you're like, you must be using this for something. And it turns it's kind of once you apply it to, for instance, if you take a p-adic field, finite Galois extension of p-adic fields, and then you apply with the G be the Galois group, and then you apply it to the multiplicative group of the top field. So there's your group, there's your module. You apply the Tate-Nakayama theorem, and it already gives you like a big piece of local class field theory. So it's the sort of abstraction that's actually being applied for something in particular. Okay, and then after that, will take us through the first 3 chapters, and then finally we'll start talking about profinite groups and Galois chromology. Anyway, yeah, I don't know. Let me know if you think that the course is going too quickly, or I guess it's technically possible, like too slowly. I've never taught a course like this before. I'm looking at a lot of pages that in theory we should cover, but of course if you cover it too quickly or if you skip too many things, then none of it makes as much sense as it should. So I'm open to feedback. All right. Well, if there are no further questions, or any questions at all for that matter, we may as well get started. Okay. So there we go. Yes, so we have this notion of cohomological triviality. This is actually kind of in relation to a question that Manzelis asked a couple of weeks ago. It addresses it anyway. One could try to extract more. So yeah, anyway, I mean, one idea is that we had these induced slash co-induced for finite groups, which implies weakly projective, which is the same as weakly injective for finite groups. And these guys were acyclic for the group cohomology, in fact, for all Tate cohomology. But then the question was, are there more objects that are acyclic for group cohomology? And this is addressing the question in a sense, because we'll see that a weakly projective module over a finite group actually has a stronger property than just being acyclic for the group cohomology. So that's one way to come at this. Right. Anyway, so another motivation. Let me try to motivate. So there's one kind of nice theorem that I will state early on in this lecture. The proof is like after 9 pages or so, so I'm sure I won't get to it in this lecture. But I want to kind of motivate it a little bit. So again, we know so much about the cohomology of finite cyclic groups, right? Those are easier. So suppose you have a finite cyclic group and then you have a G module. So we gave a kind of complete classification of the Tate cohomology. And we showed in particular that it's 2 periodic. It only depends upon whether the index n is even or odd. Well, so as one consequence of that, if you have, in this case, if any 2 consecutive Tate cohomology groups are trivial, well, since it's 2 periodic, they must all be trivial. Okay, so that's interesting. And so you could ask yourself, is that true for Tate cohomology of other finite groups? And it is, actually. And even so, that's part of what we'll prove. And even more is true. The more is a kind of local in the group theoretic sense approach to group cohomology, which is very important and very useful. So to motivate that, I actually need one of these results, a very simple result. So suppose I have a group, doesn't have to be finite, although mostly for the rest of this lecture it will be finite. I have a subgroup of finite index n. Then I take a prime number that does not divide the index of the subgroup, and then I look at the restriction map from the group to the subgroup. So in general, restriction kills stuff, but in this particular situation, if you restrict to a subgroup of finite index n, then the restriction map kills no p primary torsion in this group. These groups are, if G is a finite group anyway, these groups are torsion groups, as we saw before. So if p is prime to the index, then restricting to a subgroup of index prime to p kills no p primary torsion. So that's the statement in general. And then if it's finite, you can make exactly the same statement for all the Tate cohomology groups. Okay, so the statement is kind of interesting, but the proof is immediate. So again, in either context, we know that if you restrict and then you co-restrict, then that becomes multiplication by the index of the subgroup. And okay, so I'm looking, suppose I have a p primary torsion, an element that's killed by some power of p in the cohomology group. If it's killed by restriction, if it restricts to 0, then you follow with a co-restriction of 0 is still 0, and therefore you find that anything that was killed by restriction is killed by n. But if you're killed by n and you're killed by a power of p that's prime to n, well, that's it. You're 0, right? If you're an element of a torsion group, which is if you're m torsion and you're n torsion and m and n are relatively prime, then you must have been 0. Okay, so it's an easy proof, but the implications of it are quite profound. Okay, so again, let me try to just to try to give some narrative structure to this. Let me try to motivate this again using what we already know. So all right, if I have a finite cyclic group, I know I can write the n, the size of the group, as a product of prime powers. I'm a number theorist after all. I can do that. And so suppose now a little bit more. Suppose I have a G module that for 2 consecutive values, the Tate cohomology is 0, but not for the group itself, just for all of the prime power subgroups of the group G. Okay, so here I guess, all right, I'm doing something. My notation is not perfect. I mean, it's not really a problem, but here when I write this, I really mean the subgroup of order pi to the ai of this group G. The way I've written it, like this thing should be a quotient of this group rather than a subgroup, but of course there's a unique subgroup of that order. So the claim here, I mean, again, it's going to follow from it follows from what I just said. So again, you can look at the p primary parts of your finite cyclic group, and again, it just follows immediately. So you find if you restrict to these guys, then the index is prime to this prime p, and so therefore the pi primary torsion in each of these groups is equal to 0. But the whole group is order of G torsion. So if you have no p primary torsion for all p dividing the order of your finite group, then you're 0. Okay, so again, this is just a motivation for the main result that I want to prove. But again, if you think about this, what am I really doing? These groups are commutative, so you could think of it in terms of primary components. For a non-commutative finite group, what I'm doing is I'm restricting to the CELO subgroups. Okay, and so that's what's going to get generalized in what happens. Okay, yeah, so we'll prove a generalization of this kind of result to all finite groups G, which will turn out to be, apart from some not so exciting stuff about cup products and bilinear pairings, this generalization will be most of the content, I think, of the Tate-Nakayama theorem. Here comes a key definition, though, which is of some interest in itself. This is what I was alluding to before. So if I have a finite group G, a G module is cohomologically trivial. This turns out to be a lot to write. If it's acyclic for cohomology, but not just for the group itself, but for all the subgroups of the group. So that's stronger. Okay. So cohomologically trivial means all the higher group cohomologies of all the subgroups are equal to 0. Okay. So again, I think there should be a G module that's acyclic for G cohomology, but is not acyclic for H cohomology for all the subgroups H. But I haven't really thought concretely about how to construct such a thing for some choice of G. All right, so let's begin. And so the first thing I want to prove here is that, again, there's a hierarchy here. I'm realizing we have all these different kind of classes of modules that are in implications between them. So weakly injective, that means a direct summand of a co-induced module. But if the group is finite, co-induced is the same as induced, and therefore weakly injective is the same as weakly projective. You can have it either way. So these modules are cohomologically trivial. Again, cohomology always commutes with finite direct sums, so don't worry about that. And so you immediately reduce to showing that a module which is either induced or co-induced, you can have it either way, is cohomologically trivial. So this is a nice, I've begun to become enamored of this notation that I made. I think I introduced this in the last lecture. It really, I mean, it's just notation, but it really seems to kind of point you in the right direction. So by definition, a G module is induced if it's isomorphic to ZG tensor X for some Z module X, unless otherwise mentioned tensor products are over Z. Okay, and so my notation for ZG tensor X is XG. As I introduced this in the last lecture. This is some kind of generalized group ring. Okay, you can think of this as being this is isomorphic to the direct sum of a bunch of copies. Why do you denote it like this? Because you think about what this thing is, and it's isomorphic to the direct sum of a bunch of copies of X indexed by G. Okay, so if that's the case, then for any subgroup, okay, But this is actually kind of similar to something that we've already done, but okay. So I look at ZG as an H module, ZH module. It's a free ZH module with basis given by cosets of G and H. So you do this, and then you distribute out your tensor product. Again, I think this identity I found in my notes previously, but then you look at this and you say, aha, using my fun notation, this is this group bracket H. And so therefore XG is visibly an induced H module. Okay. So if you're G induced, then you're H induced for every subgroup. And then again, induced modules are acyclic for group homology by Shapiro's law. Okay. So here's the theorem. Okay, so it's a bit of a mouthful. So this is the theorem that at the end of several pages we're going to prove after proving several other things on the way. So I have a finite group. I have a G module. So part A. Suppose that for all primes dividing the order of the group, there exists some integer q, which this is even a wrinkle that I didn't introduce before because I thought it was too much. There's an integer q which is allowed to depend upon the prime in general, such that when you restrict to GP, you have two consecutive Tate cohomology groups of A being equal to 0. And okay, I forgot, what is GP? GP is going to be my standard notation. If G is a finite group and P is a prime number, then by GP, I will denote any P-CELO subgroup of G. Okay, so by the CELO theorems, there are multiple CELO P subgroups in general. They precisely fill out one conjugacy class. And so this isn't quite well defined. And then I can't do everything. So a little standard compatible pair argument that you can find on page 57 of the textbook will explain to you why group cohomology, or for that matter, group homology of conjugate subgroups of the same group is isomorphic. Okay. So I really can replace, if I take a group and I pass to a subgroup, I really can replace it with a conjugate subgroup. It induces the isomorphism is canonical upon choosing something that conjugates the first subgroup to the second subgroup. Okay, so don't you worry about that. It really is safe to grab any P-CELO subgroup of G. Okay, so that's a hypothesis. Okay, so our hypothesis is like a local version. It is a local version of what I said before of having two consecutive Tate cohomology groups being equal to 0. So first of all, this hypothesis is going to be weaker than just assuming that the two consecutive Tate cohomology groups are equal. And so in particular, this is going to imply that if the two consecutive Tate cohomology groups are trivial, then all the Tate cohomology groups are trivial, and then it's kind of a local version of that. Okay, yeah. So the conclusion is that A is cohomologically trivial. Moreover, kind of useful write-on. The only thing that would stop A from actually being a projective ZG module is that if you think about it, if A is a projective ZG module, ZG, then it's direct sum end of a free ZG module. ZG is a free Z module. So a projective ZG module must be a Z submodule of a free Z module. So it has to be free as a Z module. Okay, so every ZG projective module is Z free. And so conversely, though, if this module, which has this cohomological triviality property, if it's Z-free, then it's actually projective. Okay, and then there's a useful converse, which I guess I was alluding to before. Conversely, if you know that A is cohomologically trivial, no, I wasn't alluding to this before. If you know that A is cohomologically trivial, by definition, cohomologically trivial means it's acyclic for H cohomology for all n greater than or equal to 1. And here we're saying that actually it's acyclic for Tate H cohomology. So all the n's, both positive and negative, are equal to 0. So yeah, cohomologically trivial implies and therefore is equivalent to the Tate cohomologically trivial. Okay, so yeah, so there's a lot of good stuff in this theorem. Let me just take a breath, and you can ask any questions if you want. Okay, so that's the theorem that we're working towards. Okay, which again is introducing CELO theory into the cohomology of finite groups among it. Actually, let me just stop and think for a second. There's something I want to think about. Yeah, so now I'm realizing that I said that this condition was weaker than if I just replaced these guys by G's, and I'm wondering whether that's actually true. Maybe I shouldn't have said that. So that's kind of what I was thinking about. So until further notice, strike that remark from the record. So if all I assume is that two consecutive G cohomology groups are equal to 0, yeah, I don't have a counterexample in mind, but I'm not sure how you get from the yeah, so this is kind of like a local to global part, and the global to local part has to maybe I shouldn't have claimed. Okay. Anyway, so this is the result that we want to prove. Right. Okay. And so, yeah, so there's some intermediate steps, and I was sort of looking at this yesterday, and I was like, all right, this is which 20% of this material should I present? And I was like, I like all of it, so maybe I'll present all of it, see what happens. Okay, so it begins in a very fun way. So if you have a finite P group, and you have a G module, which as its underlying commutative group is a P primary torsion group, then, and it's non-zero, then its G invariants are non-zero. Okay, this is just, I mean, a nice, beautiful result comes up in a lot of places. Okay, so again, it's the non-triviality. If the module itself is non-zero, then the G invariants are non-zero as long as you have a P group acting on a P primary G module. Okay. So the main step in this is a group theoretic argument that I promise you've seen before, and I'll show you how it comes up. And then just the preliminary step, I would like to reduce to the case where A is actually finite. And so since G is finite and A is a torsion module, if you just think about this, then like any finitely generated G submodule of A is going to have to be finite, because how do you make the G submodule generated by a finite set of elements? Well, you take the orbit of the group on those finitely many elements, and then you take the subgroup generated by it. That's how you get a ZG module generated by finitely many elements. Since the group is finite and you started with finitely many elements, if you close up under G orbits, you'll get finitely many elements. And then I have a finite set of elements inside a torsion commutative group. And so the subgroup generated in a torsion group, the subgroup generated by a finitely generated torsion group is finite. Okay. So if the since A is not 0, then there must be a non-zero finite G submodule. Okay, that's what this argument is. So take any non-zero element, take the G submodule generated by it, that will be a non-zero finite G submodule, call it B. And okay, so if I can do the finite case of this result, B is still a P primary G submodule. So if even the G invariants of B are non-zero, well, then the G invariants of B are certainly living inside the G invariance of A. And so sure. Okay, anyway. Easy to see that it's enough to do the case where you're finite. And so yeah, what's the result here, this familiar result? So now suppose I have a finite group acting on a finite set. So again, X really is just a set. So the action may not be Z linear. That doesn't make any sense. It's just a set. And suppose that the size of the set is, finite P group. Okay, so lots of P's. I have a finite P group acting on a finite set whose size is divisible by P. Then the number of G fixed points is also divisible by P. Okay, so I'll remind you where you must have seen something like this before, but the argument is very easy. So, G acts on the fixed points. Every fixed point is an orbit, so G also acts on the complement of the fixed points. And so, well, it acts non-trivially on every non-fixed point. So by the orbit stabilizer theorem, every orbit in here has size a power of P, right? Because every orbit is isomorphic to, G modulo some proper subgroup, which it's a P group, so it has size a power of P. And so, okay, so therefore P divides this guy, which is the cardinality. So P divides the cardinality of X minus the cardinality of the number of fixed points. Well, I did assume that that X was divisible by P, and so therefore this last thing is also divisible by P. Okay. And then that's enough, because if you just apply this argument to G acting Z linearly on our finite P primary G module, then you get the result. And why would you have seen this before? Sorry, I don't know why that's a little hard to read. The same argument will show you that a finite P group has non-trivial center, which you see in standard group theory courses, right? And so there you just have, what do you have? You have the finite P group acting on itself by conjugation. But it's the same. The same. You look at this same lemma and you say, oh yeah. So the number of fixed points of the group acting on itself by conjugation, that's the center of the group. You have one element, the identity. Anyway, you see. So you've seen this before. It's just a beautiful, easy result about P groups acting on certain finite sets. And so in passing, just to fill it in, now we have some nice exercises that I took these from Harari, some slightly modified. So I proved a nice result that if I have a finite P group acting on a P primary G module, then the obviously if A is 0, then AG is 0. So if it acts on a non-zero P primary torsion G module, then its G invariants are non-zero. You could ask the same for the co-invariants, right? Exactly the same question. If the co-invariants are non-zero, does that imply that the module is non-zero? And no, but something is true. Okay. So yeah, so two exercises, which again I'll write down and stick in the notes. This is literally one of the, maybe this is from chapter 2 or something. So I have any group, I have a G module. I'm going to define this kind of dual, which is the Hom from A into Q mod Z. So this is, I don't know, maybe later in the course or earlier in your life, you've met some kind of Cartier dual. So it sort of looks like that, or maybe anyway, some kind of dual group. And we make this into a G module in the usual way. Whenever I have a Hom between G modules, I put the, G inverse phi G, G phi G inverse. Anyway, the adjoint action on the Hom. So I had the G action on A, and then I just put the trivial G action on Q mod Z. Anyway, so this becomes a G module, and then the part A is already all you need for the application. Part A is to show that in this sense, zeroth group homology and zeroth group cohomology are dual to each other, in the sense that the zeroth cohomology group, its dual in this sense, is the zeroth cohomology of the dual group. And I believe this is true for any group G. And now if G is finite, this duality persists. in fact this is kind of, maybe should have said this sooner, but this is an actual duality between group homology and group homology. Okay. So interesting. Why are we saying this now? Well, the next exercise is, so you take a finite P group and you take V to be a P torsion G module. So note, not P primary, actually P torsion. So that's a stronger hypothesis. And then I claim that if you just apply part A is some result which is relating which is relating the H0 the covariance to the invariance, so it seems clearly relevant, right? So I claim that if you apply part A of this exercise and the result that we just proved, that if the covariants are non-trivial, then if the invariants are non-trivial, then the original module is non-trivial. You plug that in the duality, you're going to get the same thing for the covariance. And this is actually kind of interesting. I claim there's a connection with Nakayama's lemma here, not the Tate-Nakayama theorem, the actual, well, I was going to say the Nakayama's lemma that you learn in commutative algebra, but you're going to apply this to, so I think the ring that you want to apply this to is the group ring FP of G. So Nakayama's lemma holds for non-commutative rings as well. So in the case where V is finite, I think you can also deduce this from Nakayama's lemma. So that's kind of cool. And then, but so why did we restrict to, and again, for the theorem about the non-triviality of the invariance implies the non-triviality of the module, we took a P primary guy, and then for that exercise, we took a P torsion guy. And in fact, you need to do that. So Harari, if you look in Harari, he kind of tells you exactly what the group should be and what the module should be. So maybe he ruins it a little bit. But so you can look back. But so by example, there is a finite P group that acts on a P primary torsion G module, and the G module is non-zero, but its co-invariants are 0. Okay, and already G equals Z mod 2 will work, to give you such an example. Okay, so things really don't work as well for the co-invariants as they do for the invariants. Okay, now we move on. Okay, so now, again, this is kind of in the French style. So I have a bunch of lemmas. They're all nice. And then slowly we're going to make our way towards this big theorem that I introduced before. Okay, so let's see. Yeah, this is just a relevant. This is another lemma that my notation for induced modules makes it fun. So I have two G modules A and B. If G is finite, which is really the case that we care about, and B is induced, then the G module that you get, again, same convention. If I do a Hom and I don't tell you otherwise, I mean the Hom is Z modules, right? If I do a tensor and don't tell you otherwise, I mean the tensor is Z modules. Okay, so the Z Hom from anything into an induced module is going to be induced if G is finite. And then in general, if A is projective as a ZG module, then A tensor B is weakly projective, namely a direct sum end of an induced module. Okay, so let's just do it. Just a fun little exercise. So if B is induced, then it's isomorphic to XG, by which I meant for the third time, ZG tensor X for any and all, whatever commutative group X that you want. And okay, well, let's look at the Hom. I'm being very pedantic about this. So here's the Hom, right? So B is XG. As I said, XG can be viewed as the direct sum of a bunch of copies of X indexed by G. Now, the only thing I'm doing from here to here is I'm exchanging the direct sum for the direct product. Okay. Why am I allowed to do this? What do you want?
Because G is finite?
Yeah, because G is finite, right? So in general, the direct sum over something infinite is much smaller than the direct product. So that's why I'm calling attention to the fact that I am using that G is finite. And I really do, I mean, I wanted the direct sum because that was the definition of induced, but here I want the product because the Hom of this guy is equal to the product. What is this? This is nothing else than the universal property of the product, right? So the Hom into a product is determined by the Hams into each of the coordinates, right? I mean, everybody, I hate to say, I shouldn't say everybody knows that, but that's a very simple fact about the direct product, right? The universal property of just the Cartesian product. But of course, again, it really had better be the direct product and not the direct sum for that to be true. Okay, so I pull it out. And then I say, oh, thank goodness G is still finite. So I can, you see how careful I'm being. I'm just emphasizing that this works because G is finite. And then I replaced the product with a sum. Okay. And then what is this? This is the direct sum of copies of something indexed by G, where the G action, if you suss it out, is permuting the components. And then you get that. And so then, yeah, so then you're going to get that this is isomorphic to the induced guy. Okay, so that's part A, right? Actually, as I write it down, I think maybe I'm using the fact that the co-induced module is isomorphic to the co-induced module when you make the underlying G module trivial. So flip back. Yes. I'm using this. I had something that had a non-trivial G module structure, and then I co-induced it as though it had a trivial G module structure, but they're the same. Okay. All right. So yeah, okay. So right, and so now let's do part B. So if A is projective, then I want A tensor B to be weakly projective. So right, so if A is projective, then it's direct sum end of a free module. What is a free module? A free module is an induced module where the group that you're tensoring with is a free Z module. Okay, so again, that's one way. If you think that through, that's one way of viewing. That's one way of viewing free ZG modules. Okay, and so then if you just carry through the tensor, that's gonna work out nicely. So right, so if I take A tensor B, direct sum A prime tensor B, well, that's the same as A direct sum A prime tensor B. A direct sum A prime was FG, this particular type of, in particular, an induced G module, then I tensor with B, but F bracket G was ZG tensor F. The tensor product is associative, and so that's F tensor B of G. So sure, this thing is induced. Therefore, A tensor B was a direct sum end of an induced module, so it's weakly projective. Okay. All right, and so now, okay, now we're getting somewhere. The next result here is that I have a finite group and I have a G module. So this being homologically trivial is something that you can check by restriction to the CeLO P subgroups. That's what this result is saying. And it's really not a big deal. So here I'm saying for all primes P, you restrict to a CeLO, pick your favorite CeLO P subgroup, as I explained, it doesn't matter. That's homologically trivial. And here I'm saying for all P dividing G, the equivalence of 2 and 3 is really immediate because, of course, if P does not divide G, then the CeLO P subgroup is trivial. And so everything is homologically trivial when you restrict to the trivial group. So certainly 2 and 3 are equivalent. Moreover, certainly 1 implies 2 because homologically trivial means you're acyclic for H cohomology for all subgroups. And so if you're acyclic for H cohomology for all subgroups, you're acyclic for H cohomology when H is a CeLO P subgroup. Okay, so the matter of this is to explain why if for every prime dividing the order of G, you are when you restrict to the CeLO P subgroup or any CeLO P subgroup for that prime, you're cohomologically trivial. Why does that imply that you're cohomologically trivial overall? Okay. So, okay. So what do we have to show? We have to show that, well, that for any subgroup, you're H cohomologically, you're acyclic for H cohomology. Okay. So now I take HP to be a CeLO P subgroup of H, lots of CeLOs going on. So of course, CeLO P subgroup is in particular a P subgroup. It's a P subgroup of H, and H is a subgroup of G. So H is a P subgroup of G. And so again, by one of the CeLO theorems, every P subgroup of a finite group is contained in some CeLO P subgroup. Well, again, if I'm okay with replacing any of the CeLO P subgroups by its conjugate, which I said that I am, then I can inject injective homomorphism from HP into GP. In other words, I can view HP as a subgroup of GP. But I said that the group is GP homologically trivial, and so therefore, for any subgroup of GP, it's acyclic for cohomology, so I get that. Okay, now probably I'm going to apply the lemma that I proved at the beginning. Yeah. So since HP is a CeLO subgroup of H, what does that mean? It means its order is the largest power of P that divides the order of H. Great, that means that P does not divide the index of HP in H. And that was the key according to the first lemma that we proved, because the first lemma says precisely under this situation, if you restrict to your subgroup whose index is prime to P, then you kill no P primary torsion. Okay. But now we're restricting to something which we just said was 0. So what did we learn? We learned that for all primes P dividing the order of G, and any subgroup H of G, the cohomology groups have no P primary torsion. But again, if you do cohomology for any finite group, just by the restriction, because restriction to the trivial subgroup is 0, and then composing with co-restriction, you get multiplication by the order of the group. Certainly, all of these H cohomology subgroups are H torsion, order of H torsion, and therefore they're also order of G torsion. And so yeah, so if you check that these groups are have no P primary torsion for all P dividing the order of G, then they have no P primary torsion for all P dividing the order of H, and so they must be 0. Okay, so that's kind of the most basic. Yeah, so what did we just prove? We just proved that you can check cohomological triviality by restricting to CeLO P subgroups. Okay. All right. Any questions? Okay, so now I have another theorem. I think. Oh, I think this is this the theorem before the theorem that I wanted to prove? It is, I think. Okay, so we're getting closer. So what does this theorem say? Now we have a finite P group, and we assume, again, the stronger assumption that we have an actual P torsion G module, okay? And if you think about this, if you're a ZG module and you're killed by P, then you're a Z mod PZ G module. That's not super profound. You're killed by P, right? So yeah, so I'm really assuming that A is an FP of G module. And now in this case, if I suppose that there's just a single index such that the Tate cohomology vanishes. Okay, so this is even before I was saying in the theorem I haven't proved yet. I'm saying that if you assume the Tate cohomology vanishes for 2 consecutive indices on the CeLO subgroups, then it's all of them are 0. Here I just have one index, but I'm making the stronger assumption that the module is p-torsion. Then the strongest possible conclusion you could ever want out of A comes out of this. Then A becomes a free FP of G module. Okay. And again, maybe I should explain this first. A free FP of G module is an induced Z of G module, and therefore it's chromologically trivial. So I may as well explain that now. That's another sort of similar type of argument. So why is that? Yeah, so if you're a free, no, I guess it's actually pretty easy, because a free FP of G module is a direct sum of copies of FP of G, after all, and a direct sum of induced modules is an induced module. That's no problem. And so you just reduce to the case that FP of G is induced, and then my notation is great because an induced module is something of the form X bracket of G for any commutative group X, and well, FP of G the X happens to be FP, which is a ring, but sure, yeah. So FP of G is ZG tensored to Z mod PZ. Okay. So if you can prove that it's a free FP as a FP of G module, then it's induced as a ZG module and therefore chromologically trivial. Stop. Okay. So this proof is going to take a little while, but I think it's nicely illustrative. So before we even start the proof, I want to introduce a dimension shifting formalism. Maybe this is the first I've sort of said dimension shifting, but I haven't really done like a good application of dimension shifting yet. So here's a very nice instance of dimension shifting. So recall that for any G module, we can canonically embed it into a co-induced G module, namely sort of the co-induction of itself, or where we make the underlying group trivial. Doesn't matter. So everything canonically embeds into co-induction of itself, where the map is like you send X to G goes to G multiplied by X. So you have a canonical injective G module map. And then dually, every G module is canonically surjected onto by an induced G module, again, kind of the induction of itself. And the map here is just taken induced by G tensor M to Gn. Okay, so we saw that already. Now, if you give me a G module A, I'm going to define a sequence, a Z-indexed sequence of other G modules that are helpful for doing dimension shifting. So, okay, A0 is A. A1 is going to be the co-kernel of this injective map. So it's going to be the co-induced thing modded out by M. What's the idea? If G is finite, then both induced modules and co-induced modules are acyclic for Tate chromology. So, if injecting something into a co-induced module is going to give me a short exact sequence, this thing into the co-induction, into the co-kernel, and then when I take the Tate chromology of that long exact sequence, because the co-induced thing is trivial for Tate chromology, it's going to identify the Tate chromology groups of M with the Tate chromology groups of the co-kernel, but with a shift in the index. And exactly the same thing is going to happen here. Okay, so let's see what's happening. So we define A1 to be the kernel of iota, then we continue in this way. For Q greater than or equal to 0, I do Q plus 1, so kind of twist it more to be whatever I did, twist Q times, and then I should add one that's really twist. Apply it Q times and then do it one more time. So that defines AQ for all positive Q. And so now let's wait. That should be the kernel of this map, which I'm calling Q. And now I see I'm using Q for too many things. I don't know. I'll do lowercase capital Q. Okay. So A minus 1 is going to be the kernel of this surjective map. Okay. And so now I run them in the other direction. And so if I have an AQ and I want the next smallest one, then I apply this construction. Okay. And so what do we see from this? One thing just for the application, you immediately see that if you started with a p-torsion module, which is what we're doing, then each of the AQs is going to be torsion. Because if M is p-torsion, then you check immediately that this co-induced guy and then this induced guy are also p-torsion, and then subquotients of p-torsion things are p-torsion. Okay. Right, and so again, as I was kind of saying without writing, if you just write down the Tate chromology sequence associated to these maps with the kernels and the co-kernels, and you use the fact that co-induced, co/induced is the same thing when G is finite, G modules are acyclic for Tate chromology, then you find that for all pairs of integers Q and R, the Qth Tate chromology of GA is the Q minus Rth Tate chromology of AR. Okay, so this is a very pure form of dimension shifting for Tate chromology. Okay, if you're just like, I would really love for my Tate chromology group to have a different index than it does, well, you can make it happen. Okay. All right, so let's begin. Yeah, am I even going to make it through the proof? Maybe not. Trying to decide. Well, yeah, I should. The show must go on. Okay, so let's begin. So I want to. The first thing I want to do is I want to construct an induced FPG module V such that the G invariants are isomorphic to the G invariants of A. And then somehow I want to extend the isomorphism from VG to V to an isomorphism from V to A. That's my strategy. Okay. And then that will certainly show that, yeah, maybe I clarify this by saying it's actually, yeah, so we're actually going to get a free FPG module. And so, yeah, so I do that. And then later on, I'm going to extend my isomorphism from VG to AG to an isomorphism of G modules from V to A. Well, then therefore A is isomorphic to V, which is a free FP of G module, which is what I wanted to prove. Something in the chat. Oh, okay, bye. All right, so, right. So since G is finite, this is a generalization of the thing that Tyler solved and he just left. So I think we mentioned this before already. If you take the co-invariants of any induced module under a finite group, you get the X. This is a generalization of taking the co-invariants of ZG. When G is finite, you got what we said was that you got the subgroup generated by the norm element. Okay, but what did that really mean? It basically means that if you think of elements in this, module group, whatever, this XG thing, you think of them as formal finite sums XG indexed by the elements of G, where if G were infinite, all but finitely many of them would still be 0, and each XG lies in X, then the norm element in the actual group ring ZG was corresponding to the case where all of these coefficients were equal to 1 in Z. Well, we're not working in Z, we're working in X. And so the mild generalization is that the G invariants, G is really acting on this thing by permutations, right? So again, it's just a bunch of copies of X permuted transitively by G. And so in that case, the invariants are the ones that are the same in every coordinate because G is just acting by permutation on the coordinates. That's what's happening. So the G invariants are kind of the constant ones, the ones that have the same value in every single coordinate. And so they must have the same value X, where X is an arbitrary element of capital X in every coordinate. And so therefore the G invariants come out as X, capital X, kind of diagonally embedded into XG as XXXXX in every coordinate. Okay. So in particular, I'm going to take my V to be AG of G, which again means ZG tensored with AG. And okay, and then I take the invariants I just said that the G invariants of XG were equal to AG, okay? And so if I take the G invariants here, then the G invariants are going to be X, which is AG. Okay. All right, now we go on a bit. Let's see. Yeah, okay, how much do I look at it once? So now I'm going to take Hom of, I'm saying Hom over FP. I could just say Hom nothing and have it be over Z because everything is a P torsion abelian group, so it's an FP vector space. Anyway, so I'm taking, maybe it's better to do it this way. So I take Hom over FP, and you know, if I'm over a field, then everything in sight, in general, Hom blank V is an exact functor when your module is injective, but I'm over a field, so everything is projective and injective. So taking this Hom is going to be an exact functor on FP vector spaces, and so I'm starting with this exact sequence. Okay, just you know, taking the invariants and injecting them into A and taking the quotient, and then I apply the exact functor Hom blank into V. Well, it's an exact functor, so I still get a short exact sequence. Okay, and these are still G modules. All right, and let's see. So by this lemma that we did earlier, we started with an induced G module, and then the Hom from anything into it is also induced. And yeah, here I'm using, if you look, V and, yeah, so V and A mod AG are both P torsion. And so again, Hom of FP is the same as Hom over Z because they just happen to be P torsion anyway. Okay, so M is equal to this, by definition, M is equal to this Hom, and by the previous lemma, Hom from anything into an induced module is again induced. So M is induced, so it's chromologically trivial. As a very special case of that, well, H1G of M is equal to 0. And why is that helpful? Right, so I take this map that I get by taking G invariants of this. This is a short exact sequence of G modules, okay? So if I take G invariants, again, the G invariant homomorphisms are the G equivariant homomorphisms. We talked about that at the beginning. So I take G invariants here, that just gives me G Hom. I take G invariants here, that gives me G Hom. And then the next one should be H1 of G of this thing, which is M, but I just said that H1 is equal to 0. So, but you take the long exact, this G invariance into 0. And so of course that means that this map is surjective. Okay, so that map is surjective. Okay, what does that mean? This, yeah, again, Hom from AG into V, G Hom from AG into V is the same if you're a G equivariant map and you're between when the source is G acts trivially, then G had better act trivially. You're only going to map into things where G maps trivially. So certainly this Hom is equal to that Hom. And to say that that's surjective, well, just literally that means, so if I have a G map from A to G, AG to VG, which I certainly do, I have an isomorphism or an equality from AG to VG, I can extend that to a G map from A to V. Okay, so that's what I get from that. So therefore, there exists a G map from A to V, so that once I restrict it to AG, it becomes the isomorphism that I constructed before from AG to VG. Okay. This is probably a good place to stop for today, or as good a place as any. Let me just look. Yeah. So the proof of this theorem takes, yeah, so the proof of this theorem that we're in the middle of is about one more page in my notes, nothing terrible. And then we have the proof of the bigger theorem that I stated at the beginning, and then that's going to take a little while too. So we have a bit further to go in this lecture. So yeah, let me just mark down where we stopped. So we stopped here. Okay, well, are there any questions? I admit we're just kind of stringing some results together to try to get to this big theorem. But I kind of like the proofs. I don't know, for whatever reason, I think the proofs are using kind of they're not that they're not that technical. They're using yeah. Wait till you see where the dimension shifting comes in at the end of this proof. It's going to be good. All right. Are there any questions? No? All right. I'll let you go. Okay. To be continued. Bye.